So I guess we are now live on YouTube, Matthias. So
very good.
So
That's important to know.
Okay, so now people are joining, so I'll probably just start the announcements, and then I'll make a presentation, then we're good to go. Bom dia a todos, bem-vindos a mais colóquio do Instituto de Física de São Carlos. A gente vai, hoje a gente vai receber o professor Matthias Vojta de Dresden. Como de praxe, né, eu vou pedir para aqueles que tiverem pergunta, que façam suas perguntas pelo chat do YouTube, e no final da apresentação eu passo as perguntas para o Matthias. Se alguém não estiver confortável, pode fazer a pergunta em português, que eu traduzo da melhor maneira possível. Tá, aí eu passo, aí o Matthias responde, a gente vai interagindo, tá, via o chat do YouTube. Tá, então agora eu vou passar para o inglês, para eu começar a fazer a apresentação do Matthias. So, good morning, everyone. So, today, welcome to the colloquium. Today, I have a pleasure to host Matthias Vojta in our program. So, Matthias did his PhD in Dresden, and then he moved to the US, to Yale, to do a postdoc. Then he came back to Germany, and then he has been to several places, first to Augsburg, then to Karlsruhe, then to Cologne, and finally to Dresden, where he has been since 2010. So Matthias is a very, let's say, he has very broad interests in the field of strong correlated systems. So mainly his research deals with strong correlations. So I mean, that's where the title. And he's also interested in frustrated magnet systems, spin liquids, quantum phase transition, impurity problems, and of course, high-TC superconductivity. So I guess we are going to hear a bit about it today. So moreover, Matthias is also head of a collaborative research center in Dresden. So this involves not only the University of Dresden, but also the Institute of Research in Dresden. And he's also head of a cluster of excellence program between the TU Dresden and the University of Innsbruck. So Matthias, really a pleasure to have you here. So thank you for accepting the invitation.
Thanks, Eric, for the introduction. Thanks for the invitation. I'm happy to be able to present, well, an overview of this relatively broad topic, which you can see in the title. And of course, also it will involve a few results from our group. So I understand that you can ask questions via the YouTube chat. So don't hesitate to ask questions even during the talk. Eric will convey them to me. And otherwise, there will, of course, be time for questions at the very end. So as I said, this is a broad topic, strong correlations, quantum criticality. As far as my own work is concerned, this has been done together with a number of people, both in Dresden and elsewhere around the world. And when we talk about strongly correlated quantum systems, and we do this here in the context of condensed matter, of solid state physics, then one way to quantify the correlations is to look at the ratio between two characteristic energy scales in the solid. One is the bandwidth of kinetic energy of the electrons, and the other is the electron-electron interaction. The bandwidth here parameterized by a scale W, and the electron-electron interaction mainly characterized by the on-site interaction U, often called Hubbard interaction. And if you look at the ratio between the two, then if this is small, then we are on the regime of weakly interacting electrons. And this is where we start from a Fermi gas, and then we switch on weak interactions. And on the other side, if we make this ratio strong, then we go to the atomic limit. And this red regime here is the one which is most interesting for us for a number of reasons. First of all, this is the regime where novel interaction-induced phases appear. And you see here a list of a few of them. This is where different ordering tendencies can compete, and this leads to fascinating things like nanoscale self-organization. This is where there are a number of technical applications in foresight, because, for instance, the materials tend to be sensitive to small changes, which makes them suitable to act as efficient sensors. And last not least, this regime is a challenge for theory, because this red regime here is not adiabatically connected to the regime of small interactions, the green one, which means there is no natural small parameter in a perturbative expansion. Now, here is what I want to cover in this talk. I first want to start with a few very broad remarks on phases of quantum matter, which deal with symmetries, topology, and fractionalization. Then I will have an extended introduction, sorry, to the topic of quantum phase transitions. And then I will come to probably the main topic of this talk, which is frustrated magnets and spin liquids and their extensions to certain non-Fermi liquid phases. And I will precisely tell you what I mean by this. And time permitting, I will at the end touch upon a time-honored problem in solid state physics, namely cuprate superconductivity. And I would like to tell you what fractionalized spin liquids and topological order may have to do with solving the puzzle of cuprate superconductivity. Okay, so let's start with something very general. When we think about phases of quantum matter and their systematics, then the traditional approach to classify those phases is by symmetries, symmetry breaking, and local order parameters. Such a classification, of course, leads to the well-known phases gas, liquid, solid, and is in a sense a internally complete classification scheme, because for every system you can enumerate all the symmetries it has, and you can state whether a given state of the system either respects or breaks this symmetry. So a simple example is a ferromagnet. So you have magnetic moments which all align along a particular direction. That means that a spin rotation symmetry in the underlying Hamiltonian is broken, and the corresponding order parameter is the local magnetization. A simple example is iron. And just to tell you that iron is not that simple, I just show here the phase diagram of iron under pressure. So there is a temperature pressure phase diagram down here. At low temperature and low pressure, this is the familiar ferromagnetic phase of iron. But you see a number of structural phase transitions here. You see different structural phases. And most interestingly, at elevated pressures and low temperatures, there is a superconducting phase. And this is work which is by now almost 20 years old, but it's still true that the nature of this superconductivity is not fully understood. Now, a somewhat more complicated example, still in the realm of symmetry breaking phases, are chiral magnets. This is where the magnetic moments, instead of being simply parallel, form a helical structure. This is shown in this picture here. And an important example is manganese silicide, which is almost a ferromagnet, but due to the lack of inversion symmetry in the crystal, the spins form this spiraling structure. Now, this is a conventional order parameter, but things can get even more complicated, or if you wish, more interesting. Namely, in manganese silicide, it has been shown that in a particular regime of magnetic field and temperature, a state which is a superposition of 3 of those helices propagating in 3 different directions is stabilized. And most interestingly, this is a picture of this particular state here. This state, which is superposition of 3 helices, can be understood as a skyrmion crystal, meaning a lattice of topological skyrmion defects in a homogeneous magnet. So this is a state which in a certain real space sense has topological properties. This field has by now exploded. This is an experimental paper from 2009 where this phase has been discovered. By now there is an entire field of skyrmion magnetism and its applications called skyrmionics, which would deserve a separate talk. Now, as I said, the Landau scheme of classifying phase transition is internally consistent, but over the last decades, we have learned that this is fundamentally incomplete. And the key word here is topology. And you certainly know that the godfathers, if you wish, of this development have been awarded the Physics Nobel Prize in 2016. So one the early examples of the manifestations of topology is the quantum Hall effect. You put a magnetic field, you put a two-dimensional electron gas in a magnetic field, in a perpendicular magnetic field as shown here, and you measure the Hall voltage if you drive a current through the sample in a perpendicular direction. And if you plot the resistivity, or if you plot the conductivity, you can plot the resistivity or the conductivity, and you see that the Hall conductivity has precisely quantized plateaus, which follow this quantization rule down here. And this number n is an integer, and it's an integer because of topology. So here, we are talking about an insulating state. The transport is carried by edge states. The number of edge states is precisely quantized. So here, this quantization is a result of topology. Now, another way to characterize quantum states, which has emerged relatively recently, is to think about entanglement. And of course, entanglement is something which you know from the physics of just two spins, which can be entangled into a spin singlet state as shown here. But if you think about many-body systems, then this gets somewhat more involved. And one interesting way to quantify entanglement is via the so-called entanglement entropy. So you imagine you have a thermodynamically large system as shown in this box. You divide this into two subsystems, A and B. And then you can discuss the entanglement between the two subsystems A and B. And mathematically, you do this by considering the full system, which is described by a pure state density matrix rho. And then you can define a reduced density matrix for one of the subsystems by tracing out the degrees of freedom of the other. And then this reduced density matrix, for this you can calculate the von Neumann entropy as shown here. And this is actually then called the entanglement entropy, because if you consider that the original system is in a product state of something in A and something in B, then you immediately see that the reduced density matrix is pure, and then this entropy is 0. Which means this here is a way to quantify entanglement in a many-body system. That's important. And one can, by relatively simple rules, one can derive that the ground state typically follows a so-called area law that is written down here on this slide, which means that the entanglement entropy scales with the area of the boundary between the two systems, which is linear system size to the power d-1, where d is space dimension. That's a famous area law, and there are interesting violations of this area law, which then correspond to interesting entanglement properties, and I will get back to this later. Now, when you characterize interesting quantum phases, then it's useful to not only think about the ground state, but also about elementary excitations. You can think about their spectrum. It can be gapped or it can be gapless. And more importantly, you can think about their quantum numbers. And of course, we know what quantum numbers are. So an electron has charge E and spin 1/2. But there are now in non-trivial many-body systems, there can be more interesting realizations. And I just highlight one example here. This is from a work in frustrated magnets, so-called spin-ice systems. There it has been shown that if you have excitations in this particular frustrated magnet, then they behave like magnetic monopoles, which means that essentially you can create excitations. And these are in this picture here are these red and blue objects, which behave like a north and a south pole of a magnet, and these can separately move through the system. This has been proposed in a theory paper in 2008, and it has since then been verified experimentally. Okay, so these were a few examples of interesting things. And the important point here is that for interacting systems, the systematics, the full systematics of non-trivial phases beyond the Landau paradigm is not fully understood. So a very important part of our work, of the global community in this field, is to think about and understand the systematics of interacting topological phases. Good. With this general introduction, I now come to quantum phase transitions. So first of all, it's important, or it's useful, to remember what a phase transition is. A phase transition is, and you can see an example here, a change in the collective properties of a macroscopic number of atoms. This phase transition here apparently happens as a function of temperature. So upon heating, water boils. Now, a quantum phase transition is a phase transition happening at t = 0, which then cannot be driven, as the previous example, by thermal fluctuations, but instead must be driven by some type of quantum fluctuations. An alternative view on this is, because now apparently we talk about ground state properties, about properties of ground state wave functions. An alternative view on a quantum phase transition is then that it involves a change in the nature of entanglement. Now let's look at a simple example. And I take an example from the world of magnetism. And the example is so-called coupled dimer antiferromagnets. So they are described by a Hamiltonian like this. We have Heisenberg interactions between local moments, which I assume to be spin 1/2. And I place these spin 1/2 objects in a regular lattice. And they form dimers in a way that there are always pairs of spins which interact with a particular coupling constant, which in these examples is called J prime, and which, for instance, can be strong. And then there is an interaction between the different pairs, which in this example here is called J, and this can be weak or can be strong as well. And what you see here in the slide are different arrangements of those dimers. There can be, this is a simple square lattice bilayer, so 2 square lattices stacked on top of each other, and these are other arrangements of coupled dimers. So common to all of them is there are spin pairs which are in some or the other way coupled by further magnetic interactions. Now, let's look at this dimer system to be specific. This is now again 2 couplings. One is called J. This is the coupling in each dimer, and J prime, which is a coupling between neighboring sites in each of the layers. And if the coupling J is much larger than the coupling J prime, then the leading effect is that 2 of the spins 1/2 want to form a singlet. These are now shown as these ellipses. So 2 spins, the 2 spins of each dimer pair form a quantum mechanical singlet state as shown here, and these singlets weakly interact. This is already an interesting state. You would call it a quantum paramagnet, because this is a state where at 0 temperature, the spins point nowhere. So this is a state where all magnetic expectation values are 0. Okay, now what we can do is we can now start from this state and we can vary the ratio J over J prime. And it's relatively easy to see, again, I go back to this picture, that if you instead make the coupling J prime large, and the coupling J small, so that's the opposite limit, and essentially we have a situation that we have 2 weakly coupled square lattices, and this is a system which is known to order antiferromagnetically. This immediately allows me to construct the 0 temperature phase diagram of this system as function of this ratio J over J prime. I go from this singlet quantum paramagnet to an antiferromagnetic nail state with spin orientations as shown here. Now, this was a 0 temperature statement. Experimentally, of course, you're interested in the physics at finite temperatures. And in order to understand the physics at finite temperatures, and I'm looking at a 2-dimensional phase diagram where temperature is here on the vertical axis and the horizontal axis has this coupling ratio. To understand the physics at low temperatures, one way is to think about the elementary excitations of the states on the left and the right. Now, this is particularly easy on this side because that's an ordered magnet, and it's known that an ordered magnet has spin wave excitations, which you can understand as the spins wiggling around their equilibrium position. Now, on the right-hand side, you have this paramagnet where each pairs of spins forms a singlet, a spin 0 state. And it's relatively obvious that an excitation is given by converting one of the singlets into a triplet. People call this triplet magnon or triplon. And then this is the object which can travel through the lattice. Okay, these are the 2 elementary excitations. Now you can understand the low temperature physics such by saying that you start from the ground state and low temperatures lead to a weak population of these excited states. And this population will be weak at low temperatures. And of course, the density of these excitations will increase if you raise temperature. And the resulting phase diagram, which you get from these considerations, looks like this. And the phase diagram looks like this because, for instance, the excitation energy on the right-hand side, which is needed to convert a singlet into a triplet, is large here if you are deep in this paramagnetic phase, but in fact vanishes if you approach this quantum critical point, because this is the point where the system has an instability towards the other phase. Which means this dashed line, which is shown here, is the crossover line where the density of excitations is small below the density of thermal excitations and large above the line. Which means the white regime on the right-hand and left-hand side is well described by this nail and paramagnetic physics, which I explained. But the elevated temperature regime is different. And this is the regime which people now call quantum critical regime. Why is this? What's specific about this regime? Apparently, this phase diagram tells you that this can be easily understood by starting from this quantum critical point. That's what this abbreviation QPT means. And now switch on temperature and then think about the elementary excitations of this quantum critical point. But the important thing about this quantum critical point is now that this does not have conventional quasi-particle excitations. Again, the right-hand and left-hand phases have conventional quasi-particle excitations. Here they are triplons, and here they are just conventional spin waves. But this is different at this point. This point instead has a continuum of excitations, which is characterized by non-trivial power laws. And as a result, this quantum critical regime, which can also be understood as the universal high temperature regime of the underlying quantum field theory, has non-trivial features in observables. For instance, there are non-trivial power laws in observables like specific heat or susceptibility, power laws as function of temperature. And dynamical observables typically obey scaling laws, for instance, omega over t scaling. And all these are characteristics which are unique to this quantum critical regime and do not occur in any of the stable phases. So do not occur in the left and the right, but only in this colored regime up here. Now, this is something which can be accessed experimentally. And there's one interesting material. Well, there are many actually which realize such quantum dimer systems, but one is thallium copper chloride. And this starts out at ambient conditions on the right-hand side of the phase diagram, but by pressure can be driven through this quantum phase transition to the left-hand side. And this has been studied in quite great detail. And what I show here are results from neutron scattering reported in this 2008 paper. And neutron scattering measures the energy of the magnetic excitations, and that's shown in this plot here. So there is the energy of the minimum energy of the excitations, minimum in the sense as function of wave vector, as function of applied pressure. And what you can see is that on the paramagnetic side, you see this the energy of this triplet magnon or triplon, which is finite and then goes to 0 at a particular point. And then there are spin waves, which are essentially gapless. They have a small gap because there are anisotropy terms. Otherwise, they would be gapless because of Goldstone's theorem. And in addition, there is a novel mode, which is a so-called longitudinal excitation mode, which some people also like to call Higgs mode, which has a finite energy and also vanishes at this critical point. So in other words, this system here is a very nice realization of this paradigm of magnetic quantum phase transitions. Okay, if you want to see theory, then for this simple system as shown here, you would write down a field theory which describes the antiferronegative order which exists here on the left-hand side. So it describes the order parameter and its fluctuations. This is essentially the form of a textbook 5-4 theory, or if you want a Landau-Ginzburg-Wilson theory. Landau meaning you have an order parameter theory, Ginzburg means you have spatial gradients, and Wilson means you have time gradients. And this is the standard form of this theory. And I will not go through all the math of analyzing this. This is something which in principle is well understood. And it can describe the quantum critical point and the quantum critical regime. And it has a number of characteristics which I've listed here. There is relativistic invariance, there's even conformal invariance. And there is actually, in a sense, long-range entanglement, which means that the area law, which I've advocated before, if you are, for instance, in 2 dimensions, this scales is not, the entanglement entropy is not strictly proportional to L, as it is dictated by the area law, but there is a correction, and this correction is universal. And this can be calculated within the conformal field theory and has been verified in numerical simulations. Okay. I just although this theory is well understood, I just want to report on a little surprise which we came across a few years back. Namely, there were numerical simulations which studied the critical properties of such systems, and they found that the system here on the left-hand side behaves differently from all the others. And that was a surprise, because usually one would expect that universality dictates that all of these coupled dimer systems behave in the same way. But for this system here on the left-hand side, it was found out that it's different, and we set out to understand this, and it turned out that here the field theory admits an additional cubic term, which usually is forbidden in all the other systems. That's a term which involves three powers of the order parameter, and then there are a few derivatives to make it compatible with global symmetries. And upon analyzing this term, one can figure out that indeed changes the universality class of the transition. Okay, now since I'm a theorist, I have this one slide on the status of critical field theories. As I said, most of these problems can be analyzed in terms of order parameter field theories. And the classical or the conventional way to do this goes under the headline of Landau, Ginzburg, Wilson. And this where you use a bosonic order parameter field. And this is something which in principle is very well understood. And this applies to insulators which have an ordering phenomenon. But then there are complications, and these mainly arise from two types of ingredients. One is there can be additional fermionic excitations. This happens in metals and also in semi-metals. And then there can be quench disorder, like defects. And what you see here is a list of various complications you can imagine. You can think about order parameters with Dirac fermions, like phase transitions in graphene. You can think about phase transitions in metals, where you have a full Fermi surface that's shown down here. And then there's also quench disorder. And the symbol here in front, plus, 0, and minus, is supposed to show our level of theoretic understanding. And you see that there are a few pluses, a few zeros, and a few minuses, and there is ongoing research in a number of these fields. And while the physics for insulators is well understood, the physics for metals is still not understood, in particular in dimensions below 3. Okay. I just want to mention one interesting development of the last 10 to 15 years, which goes under the headline of ADS-CFT. Some people also call this holography. And that is about the relation between condensed matter and string theory. So one idea which underlies this approach is that one can interpret the direction of renormalization group flow. And renormalization group here refers to a coarse graining procedure which theorists like to use if they want to access longer and longer scales in the system. You can interpret this direction of RG flow as an additional direction in your system. And theorists, of course, also like to think about time as an additional direction. And now it means that one can now define a space which contains D, where D is a number of space dimensions, plus 2 dimensions. Again, one additional dimension being time and the other being the direction of the RG flow. And this leads to think about theories in a space which is in D plus 2 dimensions, and demanding invariance of the metric under scaling transformations yields a particular metric which is known under the name anti-de Sitter. And that's why this is called anti-de Sitter space, and that's why this is called ADS-CFT correspondence, where ADS stands for anti-de Sitter and CFT stands for conformal field theory. The idea of this approach is now to have a relation between a conformal field theory, which lives in D space dimensions and one time dimension, to a dual theory, which is a gravity theory, which lives in this particular anti-de Sitter space. And I'm not an expert on this, but there is a large literature which actually explores this idea of holographic mapping. So you essentially have a quantum field theory which you are interested in, and a gravitational theory where you can do computations. Then you deduce results for the quantum field theory from results in the gravitational theory. And there has been some success to this method, and there's a continuous flow of publications coming out from this. So this is a useful procedure. Good. And finally, to wrap up my discussion of quantum criticality, I just want to mention one additional aspect, namely, there is often the possibility that near quantum critical points, novel phases emerge. This happens because a real system often possesses a hierarchy of energy scales, and near the critical point where the system is, in a sense, undecided of what it should do, small perturbations or weak interactions can become important. So if you have a phase diagram like this one, where you have one axis temperature, one axis the non-thermal control parameter, you have an ordered phase over here, you have a quantum critical regime here in the middle, then these residual interactions often lead to an instability of the quantum critical physics, such that there is a new phase emerging in the vicinity of this point. An example encountered frequently is superconductivity. And what you see here is a phase diagram of one of the materials where this is seen. This is a particular heavy fermion metal, cerium, palladium to silicon 2, which has as function of temperature and pressure an antiferritic phase, which disappears in a would-be quantum critical point, which is somewhere here. But this quantum critical point is masked by superconductivity. And there is a huge amount of literature on the physics of this superconducting state, which is very interesting, but I will not discuss this further here. Okay, there's one more thing, which perhaps is quite astonishing. Namely, I encountered a paper with this spectacular title, Quantum Criticality at the Origin of Life. And this came from physicists who analyzed the physics of biomolecules. And the claim in this paper is that by looking at electronic wave functions and at the theoretical analysis, one sees that they have characteristics of being near a disorder-driven metal to insulator transition, a so-called Anderson transition. This one can see it, the level statistic, the multifractality of wave functions. And so the idea, or the claim in this paper is that charge transport, which in biological system is environment assisted, there's a lot of decoherence because I mean, these molecules live in a noisy environment. That this environment-assisted transport is most effective near the Anderson metal insulator transition because there the system is most sensitive to environmental effects. And so the idea is, or the claim is, that actually many of the biologically relevant molecules are in the vicinity of an Anderson transition. This requires fine-tuning, and then this would mean that the evolution must have selected critical states. Now, this is the interesting speculation. I can't judge whether this is valid or not, but at least it's food for thought. Okay, now, this brings me to the second part of my talk, which is about spin liquids and their descendants. Now, down here, you see a picture of spin liquids, and we can do this a little more scientific by saying that a spin liquid is a ground state of magnetic moments in zero field, which does not break any symmetries. So one ingredient which one can use for that is a singlet. I already mentioned, if you have a singlet, this is a state where spins point nowhere. And if you want to go in details, one needs to be a little more specific because one needs half-odd integer spin per unit cell, and you will see what this means in a second. Spin liquids is an old concept. It goes back to the work of Phil Anderson in the 1970s, who proposed that and he proposed this particular for the Heisenberg model on the triangle lattice, that this may realize a state which is not magnetically ordered, but is instead something which Anderson called a resonating valence bond state. And I will briefly explain to you what this is. So imagine we start from an ordered antiferromagnet like this one here. What you see is spins on a square lattice subject to Heisenberg interaction. Their ground state is antiferromagnetic. Now we add a term to the Hamiltonian, which tends to suppress magnetic order. And one way to go is to add a 4-spin ring exchange, which pictorially does what the arrows show here. It takes 4 spins along a square plaquette and rotates them either clockwise or counterclockwise. So apparently, if you start from a state like this, then by applying this ring exchange operator to one of those plaquettes, then the spins, all the spin directions are reversed, which means this term counteracts magnetism. So it's clear if you make this K compared to J large enough, then you will destroy magnetic order. And the question is, what is the resulting state? And if the resulting state is paramagnetic, then it's plausible that it's built from singlets. And what this picture shows is simply an arrangement of singlets on the square lattice, which is now spatially random. This is just a wave function. And you can, that's certainly not the ground state of the Hamiltonian, but you can start thinking about this wave function. If you apply the Hamiltonian to this wave function, then you see that what happens is that you can transform a pair of singlets like this one here to a pair of singlets like this, where this singlet have now flipped. And you can do this at various places in the lattice, and like this, and you can generate a sequence of states which all are different dimer coverings of the lattice. And Anderson's idea is now you take a superposition of all of these states. So you take a wave function, which is the sum of all possible dimer coverings, which then you can call a liquid of those valence bonds. And this is what he called the resonating valence bond state. So it's called valence bond because it's composed of these singlets, and the term valence bond is borrowed from the physics of, let's say, benzene rings, where you have pairs of electrons resonating around a C6 ring. And it's called resonant because essentially, if you apply the Hamiltonian, you have processes of this type, which you can understand as a singlet resonance. So you don't change the energy, but you have two states which couple to each other. Okay, that was Anderson's idea. That's a resonating valence bond state. This is a state which does not break any symmetries of the system because the superposition of all of these states restores translation and rotation symmetry of the lattice. There is a different candidate for a paramagnetic state, though. That's a so-called valence bond solid. Namely, you can imagine that these singlet dimers are in a regular arrangement on this square lattice, and that this is in fact the dominant component of the wave function with only small admixtures of anything else. And this would be a state so where every spin captures precisely one neighbor in a well-defined fashion. And this is a state which breaks translation and rotation symmetry of the lattice. Again, that's a valence bond solid. Solid because it breaks lattice symmetries. Now, turns out that the excitations of the two states are very different. If you think about the excitations of this RVB, resonating valence bond liquid, then you can start by breaking a dimer into a spin 1, as shown here. But then you can apply the Hamiltonian to this configuration, and then you see that by applying the Hamiltonian, you can move each of these arrows separately through the lattice. And that means that the true elementary excitations is, the true elementary excitation of the system is each arrow separately. And if you think about it, the two arrows together constituted a spin 1 excitation. So each arrow individually must then constitute a spin 1/2 excitation. So what we have here is we have excitations which carry spin 1/2, but 0 charge. And this is an object which does not occur in nature. You recall electrons have charge E, spin 1/2, but if you want to form charge neutral objects from electrons and holes, then you are bound to get integer spin. Here you get half integer spin. This is what fractionalization is about. And this is qualitatively or morally very similar to the fractionalization which you get, for instance, the fractional quantum Hall effect, where you may know that you get, for instance, objects, quasi-particles, which carry charge like E/3 or E/5 or something like that. Well, this is fractionalization, and these objects you would call spinons. Now, if you instead look at the valence bond solid, you start from an excitation of this type, but now if you apply the Hamiltonian, if you want to move each of these arrows separately, you introduce misplaced dimers like these ones here, which means that actually these two arrows are bound to each other by this chain of misplaced dimers. So there's an energy cost which is linear in the separation of the two arrows, which means eventually these two objects cannot be separated, but they are bound. This is what you would call confinement in this case. So here there is no fractionalization. Okay, this was a simple illustration of the idea of resonating valence bonds as Anderson proposed it in the 1970s. Now theory has advanced a lot. We have now a pretty good understanding of various types of spin liquids. And there is by now a large zoo of spin liquids. And this slide here shows an incomplete and unsystematic overview. Unsystematic actually because we do not understand the full systematics, as I said before. But there are various types of spin liquids. There are ones which are truly topological. They have gapped anion excitations, beasts which are interesting for quantum computation. And there are other things which essentially have something like a spin on Fermi surface. So they behave like a metal in the spin sector. So this is something which has nice heat conduction, essentially like a metal. Okay. Now these things exist in paper, and again, theoretical understanding is by now pretty well advanced. They also exist experimentally, and there are a number of experimental systems where these spin liquids can be found, and these are a number of platforms, meaning lattice structures or systems where this search has been reasonably successful. And I just want to highlight two of them. There are a number of materials, organic compounds, which live on a triangular lattice. And what you see here are two phase diagrams, temperature and pressure, of two different compounds which are difficult to pronounce, but are organic compounds which essentially have spin 1/2s sitting on a triangular lattice, or I should say, which have a triangular lattice structure and are described by a Hubbard model Hamiltonian. And what you see in all cases is that if you start at ambient pressure from the insulator, at high pressure you go to a metal. And in between, there is also a superconductor. And on the left-hand side, this insulator doesn't show no symmetry breaking down to very low temperatures. So this is a spin liquid. Whereas here on the right-hand side, there is a symmetry breaking phase transition, and the low temperature state is in fact a valence bond solid, where you have dimerization of the type as shown before. So as I mentioned, in both cases, the microscopic description is in terms of a Hubbard model on the triangular lattice. I want to mention one other interesting field of work in the context of spin liquid, which has been pioneered by Alexei Kitaev in a by now famous paper in 2006. Kitaev proposed this interesting spin model here, which lives on a honeycomb lattice, which is by now known as the Kitaev model. This features anisotropic interactions. So there are three types of easing interactions where the X, Y, and Z components interact on the red, green, and blue bonds of this lattice. So that's a model which corresponds to a strong anisotropy in spin space, which must arise from strong spin orbit coupling. And the special thing of this model is that it can be solved exactly. That's one of the very rare cases where you can do this in 2 dimensions. And this exact solution shows that this model realizes a spin liquid. And this spin liquid has Majorana fermion excitations. So these are the spin-ons, which I mentioned before, which are coupled to a static Z2 gauge field. Now, this theory proposal has triggered tremendous activities in the search for materials which realize this. And one of the best candidates by now is a material called ruthenium chloride. And I just want to highlight one recent experimental result here. This is a magnet which, because it does not only have these Kitaev interactions, but also other interactions, orders antiferronetically. What you see here is a phase diagram as function of temperature and magnetic field. There's a magnetically ordered state at low temperatures and fields. But this can be suppressed by relatively small magnetic field, and then there is interesting physics going on. And this experimental observation concerns this red regime here. And what has been measured is the thermal Hall effect. So it's a Hall effect arising from heat carriers. So in other words, you take the sample, you apply a magnetic field perpendicular to it, and then you drive a heat current in one direction, you measure the temperature gradient in the other direction. So that's the thermal analog of the conventional Hall effect. And one can actually show that if there are quantized edge channels, as in the conventional Hall effect, then this thermal Hall effect is quantized as well. It's proportional to temperature, but if you divide the Hall constant by temperature, then you get a quantized number. And the number, again, is an integer, like in conventional Hall effect. Now, this measurement has been done in this particular material, and in this red regime here, one finds, and this is now this Hall constant divided by temperature, one as function of magnetic field, one finds it to be approximately constant in this red regime, and it is quantized to a number which corresponds to half an edge channel. And that is remarkable. Of course, quantization means it should be an integer. But here we talk about a system which hosts Majorana fermions, and the Majorana fermion, some of you may know, is formally half a fermion, and therefore a Majorana fermion edge channel is as good as half an edge channel. And so this here is a new type of Hall effect, of quantum Hall effect, if you wish. And this experiment, and one must say this has, we are still awaiting an experimental, a more detailed experimental verification of this experimental result by other groups. But if this experiment turns out to be correct with this interpretation, this is probably the most important experiment in the field for a decade, because it's the most direct evidence for Majorana fermions in this setting. Okay. That's what I just said. Good. I still have a few minutes to add an additional ingredient to the physics I talked about so far. And this is charge carriers. So far, I talked about spin liquids, which are, again, phases of insulating magnets. And now I want to make them conducting. And a very simple way to do this in theory is to add a second subsystem. So I now think about systems which consist of local moments, as symbolically shown here on the left-hand side, and conduction electrons which live in an additional band, and symbolically the right-hand side is supposed to show a Fermi surface. So this brings me in the realm of so-called heavy fermion materials, where you have conduction electrons and localized electrons which interact with each other, and the theoretical description for this is Kondo lattice. And one thing which often happens in these materials is that the conduction electrons screen these local moments by a lattice version of the famous Kondo effect. And then one ends up with a paramagnetic metal where essentially these local moments have been eaten up. This is then called a heavy Fermi liquid. And this is one of the possible phases. At this point, I want to remind you, because this will become important in 5 minutes from now, about an important theorem in the theory of metals, namely Lattinger's theorem, that makes a statement about the momentum space volume enclosed by the Fermi surface. You know, in a Fermi gas, the volume which a Fermi surface encloses, of course, scales with the number of the particles. It's elementary statistical mechanics. And the statement of Lattinger's theorem is that this volume of the Fermi surface is not changed if you switch on interactions. Which means in equations that the number, that the Fermi volume, which is here on the left-hand side, is given by the total number of electrons, modulo 2, because you don't want to count full bands, because full bands don't contribute to a Fermi surface, times a number which contains geometric factors. And this thing is actually something which can be proven perturbatively, but there's also non-perturbative proof relying on if you wish, topological properties by Yoshikawa. Okay, now we return to our Kondo lattices. And if you think about this system here, then there are essentially two competing physics effects. One is that these local moments want to order. They can form an ordered magnetic state. And the other is that these conduction electrons can screen the local moments by the Kondo effect. This is physics which actually has been realized already by Doniach in the 1970s, leading to a phase diagram as shown here. Here's temperature. Here's the ratio between these two effects, namely the ratio is between the strength of Kondo screening, parameterized by a Kondo temperature Tk, and the strength of the intramoment interactions. And if the intermoment interactions win, then there is static magnetic order. This you would call a spin density wave metal. And on the other side, Kondo effect wins, and then you get a heavy Fermi liquid, which is non-magnetic. And importantly here, the Fermi surface obeys Lattinger's theorem, which means that the volume of the Fermi surface is given by the total number of the electrons, which importantly in this case is the number of these electrons plus the number of these electrons, which means if the Kondo effect is in place, then these localized electrons effectively become itinerant. Okay, so what this phase diagram does is it reflects the competition between local moment interactions and metallicity. Now, what I told you before is that there is such a thing like a spin liquid, namely this static magnetic order, which exists here on the right-hand side, can also be destroyed by frustration. And that is a situation which we considered a few years back. And we came up with a modified phase diagram here, which now applies to a situation in the presence of strong frustration. We now look at this Kondo lattice system. The phase diagram has the same axis as before. There's a heavy Fermi liquid on the right-hand side. But now we have a new phase here, which we call fractionalized Fermi liquid. What is this? This is symbolically speaking, a situation where these local moments here form a spin liquid. And this spin liquid happily coexists with the conduction electrons, and the two subsystems interact only weakly. This is a fractionalized Fermi liquid. This has signatures both of a fractionalized spin liquid, and that's written up here. The local moments form a spin liquid, which can have topological properties. There's no symmetry breaking, no order parameter, but it also has sharp electron-like quasiparticles, which come from the subsystem on the right-hand side. That means that in this phase, Lattinger's theorem is violated because the Fermi surface will only come from the C electrons and will not involve these local moment electrons. But that's an interesting phase diagram because it has a quantum critical point, or let's say a quantum phase transition between these two phases, but there is no symmetry breaking, but there is a jump in the Fermi volume. And what happens essentially is that these local moment electrons are itinerant on the right-hand side and are localized on the left-hand side. Therefore, people also like to call this orbital selective Mott transition. But that's a quantum phase transition which has a jump in the Fermi volume. And if this quantum phase transition is continuous, then it comes with critical properties. And since Fermi surface properties change, this will involve a critical Fermi surface. That's a very interesting concept, which I have no time to talk about here in much detail. But this here would be a very interesting metallic state, which has power law spectral functions on the Fermi surface. Okay. This is a theory scenario. There are a number of compounds where this has been discussed. And I want to use the last 5 minutes to relate this to the topic of cuprate superconductivity. And I will spend essentially 3 minutes in introducing you what the puzzle in cuprate superconductivity is about, at least what a particular view on this puzzle is. And then I will try to connect this to the story I just told you. So, superconductivity is an entirely rich field on its own. What you see here is a superconducting transition temperature of various compounds as function of their year of discovery. And this only goes up to 2010. Some of you might know that there is some addition here. There is hydrogen, sulfur under pressure. There are various versions of this which have a rather high TC, but again, only under high pressure. What we talk about here are these compounds shown in blue. And I just remind you that there was a Nobel Prize awarded in 1987 for the discovery of the first of these compounds. And these are the compounds which still under ambient pressure have the highest TC. Now, the interesting thing about these materials is that despite more than 30 years of research, their physics is not well understood. This is not because people have not tried, but this is because it's complicated. And the reason is that, first of all, this is a strongly interacting problem. So there are strong quantum fluctuations, low dimensionality. And moreover, it turns out to be complicated because there are many competing phenomena. And it's very difficult to distinguish universal from non-universal properties. So here is a typical phase diagram of cuprate superconductors. This shows temperature on one axis and chemical doping on the other axis. So
the systems start out, in the undoped case, from being a half-filled mod insulator. And the physics is mainly on the square lattice. So what we start with is a square lattice antiferromagnet. You've seen this picture before. That is magnetically ordered. And then upon moving to the right-hand side, we add charge carriers to the system, either electrons or holes. This is what first destroys the magnetism and then brings about superconductivity with a rather high TC of 100 Kelvin or higher. What this phase diagram shows is that there are a number of other phases and regimes. And the truth is that the superconducting phase is empirically relatively well understood. But what is not understood are the normal state properties, in particular here in the regime of small doping on the left-hand side. But the two things are important to realize. First of all, the superconductivity emerges from doping of a mod insulator. It's not just physics of a simple weakly interacting metal. The second thing is, and that is with respect to a number of phases which in fact exist here in this low doping regime, which I didn't even show in this phase diagram. There are various other orders, which in fact, again, are somewhere here down in the phase diagram, which occur on top of the so-called pseudogap state. So in some sense, the pseudogap is the most interesting and most mysterious property of these cuprates. So what is a pseudogap? The pseudogap essentially refers to a suppression of the density of states in the metallic state, which exists here, a suppression of density of states above the superconducting TC. And in measurable observables, you see this here in these two plots. One shows a tunneling density of states. That's essentially a measure of the local quasi-particle density of states. And this is a material which has superconducting TC of 93 Kelvin. And you see at low temperatures, you see a superconducting gap. That's this dip here. But this dip continues to exist significantly above TC. That's what this plot shows. This plot here shows the specific heat coefficient. So object, this should be gamma, I'm sorry, which is C over T as function of temperature. The superconducting TC in these materials is somewhere down here. It's below 50 Kelvin. But what you see is that this thing, which in a metal should be constant, starts to go down at temperatures far above TC, already around 200 Kelvin. So there are signatures of a gap, or actually a partial gap. That's why it's called pseudogap above TC. And it has never been really understood where this comes from. There are probably around 30 different theoretical proposals what it could be. But there is nothing, no explanation which convincingly explains all observations. Now here is a proposal. The pseudogap is, and that is a story which has been shaped over the last 10 years or so, is likely to be understood as the coexistence regime of a spin liquid and charge carriers which have a Fermi surface. So it will be an exotic state which has some type of topological order where a spin liquid exists with hole-like quasi-particles. So in other words, you start from a mod insulator which has local moments. These local moments persist as a spin liquid, and the doped holes form carriers which essentially live an independent life. This is technically a fractionalized Fermi liquid, which I just described to you. And then the phase diagram here would look like this. There will be this underdoped state, which is not a Fermi liquid. And this will be separated by a quantum phase transition. And the overdoped state will be a conventional metal, which is a Fermi liquid. And these two states, one fulfills Lattinger's theorem, one violates Lattinger's theorem, precisely as I told you before, must be separated by a normal state quantum phase transition, which involves a reconstruction of the Fermi surface. Now, these materials are superconducting, which means this phase transition is not visible. It's masked by superconductivity. And it's now a very interesting speculation how the superconductivity is influenced by this quantum phase transition. There are baby theories of what I just described to you, but a full theoretical description is not available because this is simply complicated stuff. I just want to show you one experimental paper which appeared relatively recently, which supports what I just said. These are measurements of the Hall effect in a particular cuprate superconductor in high magnetic fields. And from the Hall constant, you can deduce the carrier density, and this is what has been done. So in the left-hand plot, you see the Hall effect itself, and you can extrapolate the signal here at elevated fields. You can extrapolate this to zero field, and then you can come up with a Hall number, and this gives you the carrier density. And this is shown on the right-hand side as function of doping. Doping is now called P, previously it was X. And what you see is that this carrier concentration, the overdoped regime, is actually given by 1 plus P. And P here is now the deviation from half filling. So 1 plus P is the correct number of electrons. So this here is a metallic state which fulfills Lattinger's theorem. But here on the low doping side, there are various data points which are on a line where the carrier concentration is P. So this violates Lattinger's theorem. And in this regime here, you see actually a relatively sharp crossover from one value to the other, which would involve the transition which I just advocated to you. The normal state carrier concentration, as deduced from this experiment, changes from P to 1 plus P, which supports the idea of a quantum phase transition from a fractionalized Fermi liquid to a conventional Fermi liquid. Okay, with this, I just put up this phase diagram again, and then I am already at my conclusion slide, and I thank you for your attention.
So thank you, Matthias, for the very nice talk. It was really engaging. So we already have a couple of questions here in the chat, so I'll start. So Jose Oyas, he asks, I mean, regarding your heavy fermion system, where you have the fractionalized Fermi liquid and the heavy Fermi liquid, if there is if there is a superconductivity instability around the QCP, I mean, if this is a common feature of your model or not, because I mean, that's the first question. I guess it relates to this.
Yes, that's a very well posed question, and that's an interesting issue. Just go back to the slide where I showed this. We talk about essentially this situation here. We have a transition between the fractionalized Fermi liquid and heavy Fermi liquid. The answer is, in certain cases, definitely yes. And I'm not sure about whether this applies to all types of possible fractionalized Fermi liquids. So what you have to think about is the fractionalized Fermi liquid, the properties of the fractionalized Fermi liquid will depend on what the nature of the spin liquid component is. And I gave you an incomplete overview before. There are Z2 spin liquids, there are U1 spin liquids. They are distinct by their structure of the gauge fields. There can be gapless and gapped spin liquids. And in particular for Z2 spin liquids, which have an inherent pairing, and you can make this clear because the gauge symmetry goes from U1 to Z2. For Z2 spin liquids, one can reasonably argue, and we have model calculations for this, that the Z2 leads to a superconducting instability at this quantum critical point. In other words, the natural scenario is that at least for a Z2 spin liquid component on the left-hand side, this quantum phase transition will be masked by a superconducting phase. And the pairing structure will be essentially inherited from the pairing structure of the fractionalized Fermi liquid. And we actually recently published a paper where we did this, where we made this explicit for the Kitaev variant of this story. So you take a Kitaev spin liquid and couple it to conduction electrons, and then one can actually do a reasonably controlled calculation of the entire phase diagram. And there is a non-trivial superconducting phase emerging, which masks this quantum critical point. Now, whether or not this is the physics of cuprates or whether one needs to think about this differently is, of course, an open issue.
So thanks, Matthias. So I just have a follow-up question. I mean, I got this phase diagram because, I mean, when you were discussing these dimerized magnets, I mean, you nicely showed us two interesting things. So you understand which kind of excitations you have at the QCP, I mean, which kind of exotic excitations you have. And moreover, you were able actually to calculate that gamma term in the entanglement entropy. I mean, do we know something about this for this particular phase, or at least on some given models that as you just explained to us?
Not for sure. So this is territory which is too complicated. So there is baby theory for this transition. The baby theory is essentially something where you do mean field plus Gaussian fluctuations. And then there is a reasonable understanding of what can happen here, but this is not enough to get a full impression on what the critical behavior is. There is phenomenological theory. There is an interesting work by Sentil, a follow-up work in 2008. And then it's plausible, actually, that the main characteristics of the critical point is that you have power laws in the single particle spectral function. So you have something which is, in a sense, like a Luttinger liquid. So a Luttinger liquid is where you have well-defined Fermi points, but you have power laws in the spectral function. Here you would have a well-defined Fermi surface, but you have power laws. The exponents may even vary along the Fermi surface. And this is what is the most interesting characteristics of this state. Of course, from this, you would like to calculate transport properties, and nobody has done this in a controlled fashion. Your question had a second part, which I just forgot. I'm sorry.
No, I was just wondering, I mean, if there is any calculation for that gamma term in the entanglement entropy. So, I mean, because I mean, for the coupled magnets, we know we know these at least.
Well,
So
yes, this is more complicated here, because if you have a phase which is gapless, and actually here both phases are gapless, then the area law is violated anyway. So the area law in its pure form is only valid for gapped phases. And it's known that, for instance, if you have an ordinary Fermi liquid, nothing fancy, just an ordinary Fermi liquid, there are logarithmic corrections to the area law because of the long-range nature of the Fermi sea. In other words, here discussing entanglement properties is significantly more complicated and less universal.
So thanks, Matthias. So I have a question for our colleague, Carlos Eges. He asks you, I mean, to speculate on the possible relevance of the holographic principle to better discuss topological insulator or topological superconductivity. I mean, there is any work along this direction.
So disclaimer, I'm not an expert in this field, so I just tell you what I think I understand. My impression is that for systems consisting of weakly interacting electrons, there is no need to resort to holography. So in other words, weakly interacting systems, which you can understand essentially in a single particle, in a single electron picture, this is by now reasonably well understood. There are symmetry classifications around, and the systematics is, as far as I think, at least understood for fully gapped phases. For partially gapped phases, there is still ongoing work. But there is no need to resort to holography. Holography is mainly used for strongly interacting systems, where if you want to work with the conventional interacting electron theory, leaves you with the lack of a small parameter. So in other words, there are no controlled calculations possible. And the hope, and this has been at least materialized in a few cases, is that if you go to the holographic dual, then you can do controlled calculation in a strongly interacting regime to describe physics which is otherwise not computable on the condensed matter side. So in this sense, I've not seen any interesting work for topological insulators, essentially because there is no need to do any holographic computation. But there are a number of interesting works around for quantum critical magnets and also for quantum critical metals. Just recently, there was a paper which discussed actually hydrodynamic flow of electrons based on ADS-CFT analogies.
So, thanks, Matthias. So now I have another question from Jose. He's talking about cuprates, and he's asking if we could further comment on the spin glass phase. I mean, if to have this spin glass, where does the frustration comes from? And I mean, how does the transport works in this region?
That's an interesting question, and it's getting complicated. So first of all, the properties of the spin glass are not universally the same across all cuprate families. The spin glass certainly is a local moment spin glass, and that is compatible with the idea which I advocated, namely that the underdoped state is a state of this type. So you have local moments which coexist with charge carriers. And the local moments in the presence of this order, of course, in principle, can show an instability to a type of spin class order. Again, whether or not a strong spin class is realized depends on which cuprate family you look at. So the spin class is a short-range ordered state. This has been characterized by neutron scattering to some, and NMR also in some detail. The spin class, actually, this phase diagram here may not be fully accurate for all cuprate families because some actually have a long-range ordered tail here at very low temperatures. There is, in this regime, you also tend to see carrier localization, and you tend to see upturns in the resistivity which come from variable range hopping. This is now presumably coming from a combination of Coulomb interactions and disorder. And whether or not the spin class physics plays a crucial role in understanding, in describing the conductivity is something which is not known, to my knowledge.
I'll just have a quick question here, and this, because I mean, you show this nice model for heavy Fermion physics, but usually when you think about cuprates, the simplest model is just a one-band model. So I mean, how would that work? I mean, what would play the role of the localized moment, and what would play the role of the itinerant electrons?
That's a very important conceptual question about people, including myself, have thought a lot. And I just can go to one of my backup slides if I now find it. So you're perfectly right. Cuprates in the simplest model are described by one band. And then there is no natural separation between the local moments and the carriers. And one way to, let me just jump to the right slide here. One way to think about this is essentially, well, we can start from this one here. Suppose we have this spin liquid to start with. So that's now an undoped spin liquid. And then we put in holes. That is the situation which would correspond to weakly doped cuprates. Then you see that what happens is that in principle, if you dope holes, then you also get liberated spins, right? Because you destroy a dimer. And if you have a fully fractionalized situation, you might think, oh, these objects now are charge carriers, but this would be holons. They carry charge, but no spin. And these objects now, the arrows would be spin-ons. They carry spin, but no charge. This would be a fully fractionalized scenario. This has been discussed in the early days of cuprates, but is not realized according to current experiments, because experiments indicate a Fermi surface of conventional electrons which carry both spin and charge. And then what you need to think about is, instead of what I just showed, is you have to think about, oh, okay, so I don't have a good slide for this. You have to think about, instead of having full fractionalization, which is here on the left-hand side, carriers into spin-ons and holons, you think about a formation of bound states between spin-ons and holons. So the idea is that essentially in this picture, these two things recombine to form a conventional electron. And this is a picture which actually, in a nice work by Sachdev and co-workers in 2015, is illustrated by, they wrote down a particular quantum dimer model, and that is pictorially shown here. So you have dimers, but then if you put a hole, then this hole recombines with the liberated spin to form a bound state. And this is then the carrier. And there are still spin-ons in the game, which are not shown in this picture. But the holes do not become holons, but they recombine. But so there is an additional physics ingredient, which is the bound state formation, which is something one doesn't need to invoke in the two-band picture. And that this happens is not a trivial thing. But if it happens, you get a fractionalized Fermi liquid.
So thanks, Matthias. We have a question for student João. So he's asking, I mean, how can one use entanglement entropy to describe spin liquids? I mean, and if you can differentiate between different spin liquids using entanglement entropy?
The true answer is you cannot. So, I mean, I showed the zoo of spin liquids here, and I tried to get back. This will take a few seconds. And again, this was an incomplete zoo of spin liquids. this was presumably this one here. And again, the entanglement entropy, again, that's a useful characteristic for any many-body phase, which may be non-trivial. But as I said, the area law is only obeyed for gapped phases. And then if we have gapped topological phases, then we may talk about violations of the area law. And these are typically universal and described by the underlying topological field theory. This applies to the first case here. This is about gapped spin liquids. Their entanglement entropy is useful. The other cases which you see here are all gapless phases. And gapless phases, there again, you generically get a violation of the area law, which is not even universal, which means their entanglement entropy is still a useful quantity to study, but you cannot draw sharp conclusions from that. And moreover, you definitely need detailed modeling in order to make sense of it. Therefore, entanglement entropy is not enough. And what people have used beyond entanglement entropy is the entire entanglement spectrum. So what you can do, and that's not what I talked about here in this talk, you can take this reduced density matrix and essentially take the log of it, which means you can compute the corresponding Hamiltonian, which would have this density matrix as its finite temperature density operator. So this gives you, and you can then diagonalize this Hamiltonian, this gives you a spectrum that's called entanglement spectrum. And that is now something which contains a lot more information because it contains levels at particular energies. And then this entanglement spectrum, that's something which we are now essentially in the process of learning, is like a fingerprint of the underlying topological phase. Also there, the systematics is not fully understood. And at present, we are like in the area of collecting stamps. So we look at the entanglement spectrum of a particular phase, which we think we understand, compare it with the entanglement spectrum of a phase which we don't understand. And that now refers to results of computer simulations. If the two look alike, we say, oh, that's the same phase. So again, systematics is lacking, but that's definitely a very powerful tool.
So thanks, Matthias. So we have another question for student Lucas. He asks the following. So if you have a classical, let's say a thermal phase transition, and then you put frustration, typically what happens is that TC goes down. And he's asking me, what does frustration do to a quantum critical point? I mean, how does it change the energy scales involved?
Many things are possible. We can, for instance, look at this phase diagram here, which I was advocating at this point. So we look at this phase diagram here. So the way I presented it, there was an unfrustrated, well, let's say, yeah, essentially an unfrustrated magnet. It was a bilayer square lattice system. And it has nice magnetic order on the left-hand side. And now you could ask, now if I start frustrating this thing, what happens? I guess this is the essence of the question. And there are various things one needs to consider. The first question, I guess, is does this ordered phase here on the left-hand side survive at all? And if the answer is yes, so there may be a different magnetically ordered state. I mean, for instance, you can, instead of taking a square lattice, you can take a triangle lattice that's a bit frustrated, but there is still magnetic order. Then the phase diagram will qualitatively look the same way. And since magnetic order is weaker, this phase transition point here will move slightly to the right. Slightly to the left, because magnetic order is weaker. So this phase tends to be suppressed with respect to this one. That is a quantitative change, but it's not very spectacular. If, of course, the frustration is strong, such that this ordered phase is suppressed, then this phase here may be replaced by a spin liquid, for instance. So a game which we also played a few years back is you take 2 layers of a Kitaev model and play precisely this game. You have dimers on the right-hand side, and you have 2 weakly coupled Kitaev spin liquids on the left-hand side. Then you have a quantum phase transition between a paramagnetic phase, which is trivial, it consists of dimers, and a paramagnetic phase, which is topological, because it consists of 2 weakly coupled spin liquids. You still have a quantum critical point. The properties are now entirely different. It's not about a conventional order parameter. It's not about symmetry breaking. It's instead about topology. And presumably the location of the critical point also shifts, but now we are comparing apples with oranges. So it's just an entirely different thing. And there is some work has been done in this direction. There's a handful of papers or 2 handful of papers discussing those things. But experimental realizations are scarce simply because there are not so many candidate materials for spin liquids which can be nicely tuned.
So thanks, Matthias. So have another question from Carlos Eges. I guess, I'll try to wrap it up. So I guess he's asking me, how does this, let's say you have all this nice fractionalization, but most of it, we start with spin 1/2. So model with spin 1/2. So let's say try different spins. Can this still happen? What would change? How does the game depends on a spin, essentially?
That's a good question, and partial work has been done. One has to keep in mind that the work on spin liquids comes from 2 branches. One is people try to construct exactly solvable models, or almost exactly solvable models, let's say models which can be solved in a controlled fashion for particular spin liquids. And there are a few of them by now exist. And the other is people do numerics for realistic Hamiltonians and try to figure out whether a spin liquid phase is realized somewhere in a phase diagram of a given model. The numerics becomes increasingly difficult with increasing spin because the Hilbert space gets larger, which means there are good results for spin 1/2 models, there are a few results for spin 1 models, and essentially no results for higher spin. The exact models which people have considered, most of them are actually for spin 1/2, but a few are also for larger spin. The bottom line of all of this is spin liquids can exist for higher spin. So for instance, we know that the Kitaev model for spin 1, which essentially works very similar to the Kitaev model for spin 1/2, it's no longer exactly solvable, but it features a spin liquid phase, which is a Z2 spin liquid. So that's known. Numerics is good enough to say this. And there is also some work on the Kagome lattice, Heisenberg antiferromagnet with spin 1, and there are indications that this also has a spin liquid regime somewhere in the phase diagram. Of course, it's clear if you go to larger and larger spin, then finding spin liquids will become increasingly improbable because large spins behave classically and like to order. Which means if you want to look for spin liquids, you should better do this for small spin. And the Kitaev model actually nicely shows that in some general phase diagram, the regime of a spin liquid is relatively large for s equals 1/2, then it shrinks if you go to s equals 1, and whether it continues to exist for s equals 3/2 is not known at this point. So spin liquids exist for higher spin, but again, that is not a good place to search for simply because the spin liquid phases get narrow.
And just a follow-up question, this Kitaev model for spin 1, you told us it's still a Z2 spin liquid, but do we still have Majoranas in it as excitation? Can numerics tell us that?
That's a good question, and I'm not sure whether this is known. I guess what has been there are like 3 papers with good numerics on s equals 1 Kitaev, and I think, but I'm now guessing. I must admit, I'm guessing. I'm not fully aware of the entire content of these papers. I think it's difficult to really deduce what the nature of the excitations is. What numerics can give you is, ideally, if you could do exact diagonalization, you can get the entire tower of states. And from this, you might be able to deduce the content of the elementary excitations. But I don't think there is any reasonable work in this direction. I think the work which has been done is DMRG, which essentially gives you ground state properties. And from this, you can't deduce the character of the excitations. So I think it's an open issue. There are some approximate solutions which indicate that there could be Majoranas, but this is not carved in stone.
Okay, thanks, Matthias. So there is a question by Rodrigo, and he's asking if there is any material candidate to realize Kitaev physics plus conduction electrons.
Nothing which is really solid. So there are in principle, people thought about doping Kitaev materials. So there are a few Kitaev materials. One is the ruthenium chloride, which I mentioned. And then there are a few honeycomb lattice iridates, which have also been considered as Kitaev materials. All of them order at low temperature, except for a particular incarnation, which is very heavily disordered, which does not order, but that's presumably just some disorder-dominated phase. There have been attempts to chemically dope them, and they have not been successful in the sense that you get a metallic state, at least not that I know. But these attempts are ongoing. There is an interesting idea to put ruthenium chloride, which some of you may know is a van der Waals material like graphene, so you can scotch tape it to get a single layer. So people have put this on graphene. So there is an experimental paper published which has ruthenium chloride on graphene. And one idea being that with charge transfer, you may metallize ruthenium chloride. And this in principle works, but the problem, so there is charge transfer. But what you also do is you make the graphene metallic, because if you charge transfer, graphene is no longer charge neutral. And then it's difficult to separate the conduction of the graphene from the conduction of your doped ruthenium chloride. And therefore, nothing which is reliable in terms of answering the question has been achieved. But these are the attempts. And so the honest answer is no, but I would not give up hope.
Okay, thanks. So Carlos Agues has another interesting question. He's asking if there is any competing explanation from the quantum Hall plateau on the Casaharo experiment. I mean, because there has been, we had been through this already, right? We find chiral Majoranos, then we no longer find them when we find experiments. So he's asking if there is any, let's say, more mundane explanation.
That's a difficult question. And I guess one needs to go one step back when discussing this. First of all, the explanation which I gave you was oversimplified, because what I said is you get this quantized Hall effect if there is heat conduction by edge modes. However, we have to keep in mind that we talk about solids, and there is always bulk heat conduction by phonons. And that makes this very, very different from the charge Hall effect. I mean, the charged Hall effect, like the conventional quantum Hall effect, there the bulk is really an insulator, and there is charge conduction exclusively by edge modes. This is something which with heat you can never achieve in a solid, because there's always phonons. Which means the interpretation of this experiment is highly non-trivial, because you have a large bulk heat conduction, which is conventional. So there's a large kappa XX, so a longitudinal heat conduction. And there's only a small transverse heat conduction. And this is the one which is extracted here. So in other words, even if there is a quantized edge mode, it's absolutely non-trivial to see a quantized Hall coefficient at all, because the bulk is not insulating. So that's the disclaimer. And this experiment has triggered theoretical works which considered the question, is there at all the possibility to get quantized Hall effect from a quantized edge mode in the presence of bulk heat conduction? And the answer is quite non-trivial. The answer is approximately yes, but only in a regime of intermediate temperatures. And there are two interesting theory papers, which I encourage you to read if you're interested in this, which means one can, even in an ideal situation, not expect to have a perfect quantization down to the lowest temperatures, simply because of phonon heat conduction in the bulk. That, of course, lets you look with a different eye on the data, because after all, we don't expect perfect quantization. Now, this here could simply be a red herring. So in other words, this can be by accident lie in the vicinity of 1/2 and mean nothing. I mean, the error bars are not small, and it's not very close to 1/2. But there is no good explanation as to why it should be close to 1/2 if it's not a Majorana edge mode. So in this sense, I still consider the Majorana edge mode as the most plausible explanation. And there is none which, apart from saying, oh, it's an accident, would rationalize this result. What is important on the experimental front is to follow this signal here to low temperatures. You see this ends at 3.7 Kelvin for a reason which Matsuda is saying his cryostat can't go lower, which doesn't, since this is a really important problem, is not a good excuse. So one must follow this result to low temperatures. And again, theory predicts that you lose quantization in a very specific way. And this must be verified experimentally. And then we see what this is.
Yeah, there is, and Carlos, he made, the follow-up question, because, he's saying that it's generally elusive to find both Majorana and Majorana bound states. And as you explained, that's the main motivation. And I guess you nicely said, this is the most natural explanation so far, and we need to go to lower temperatures, I guess. There's a question by Christian, and she's asking, you mentioned several interesting techniques to experimentally study cuprates, and he's asking about RICs. If RICs can give some new light, what can we learn using RICs in the cuprates, if you can bring something new.
RICs is a very interesting technique which has seen tremendous improvements over the last decade, in particular in energy resolution. RICs is to some part seen as a technique which, in a sense, supplements neutron scattering, which means it detects dynamics of spin excitations. The RICs cross-section is different from the neutron cross-section, so this discussion is more complicated than I just make it. And in contrast to neutrons, with RICs, you can reach other areas of the Brillouin zone. So with neutrons, there are kinetic restrictions which make only a small area of the Brillouin zone accessible, and with RICs, you can reach a larger area of the Brillouin zone. So in other words, one utility of RICs is to have a better mapping of magnetic excitations across the Brillouin zone in situations where neutron scattering is difficult or impossible. This includes, for instance, samples which have very small volume, like few layer samples. There are neutrons, the neutron cross-section is just too small, you can use RICs instead. All this is about detecting dynamic spin excitations, and interesting work has been done. So far, the resolution of RICs has not been sufficient to tackle some of the big problems which in the field exist, but with further improvement in the next 10 years, this may change. Whether this will solve fundamental questions in the cuprate community is something which is not so clear to me, and that requires a long discussion where we should agree on what the fundamental questions are. And even this is debated, therefore I stop here. So RICs has been very useful, but the most interesting, let's say, developments actually came from transport experiments. It's at least a significant fraction of the interesting developments recently came from transport experiments, like the one I was showing.
So Matthias, I see no more questions here in the chat, so I would like to thank you once again for this very nice and engaging talk, and also for the nice follow-up discussion. This was really informative.
These were many questions.
Yes.
I'm grateful for them, and I thank you again for the possibility.
No, and this was our pleasure. So now I'll just end the transmission. So